Oh, what time is it? Oh, people waiting. Must be almost time. Oh, all right. It's 9:45. Let's get rolling. Lord, thank you for bringing us together this morning. Thank you for everything that you do for us. I pray that you would continue to watch over us, continue to give us what we need. Pray that you would help us stay focused, help us finish out the last month of the semester strong. In your name we pray. Amen. All right. Excellent. This seems like it's working. Everybody hear me okay? I've got a slightly different setup today, so that'll be good. All right, so what are we doing? All right, what are we doing? Oh, well, let's recap. We'll start with our recap. YFS, U of T, inverse matrix. Okay. At this point with the matrix stuff, if you're still not getting it, you gotta come to office hours. Okay. Watch the beginning of last class, right? We did a whole thing. You can watch it in the two different lectures that I posted, right? But if you're still not understanding how to populate the matrices, please come to office hours and we can talk about it more in depth there. Unfortunately, we do have to move through the new stuff at this point and really get through Laplace transforms. Y of S. Y of S, first of all, it's not correct there. It should be capital Y of S, right? Because when we do the Laplace transform, we get the capital, right? So Y of S, right? Well, Y of S and U of T, I'm going to save because we're going to go through that problem again and we'll go through it. And if you're still not getting it when we're going through the problem, bring it up again and we can go through it. Inverse. I'm not sure why we're talking about inverses. Um, not really sure why. I don't know where that would have come up in class, right? So all right. Is there anything else that people want to talk about before we launch into some things here? No, nothing. All right. Well, let's talk about.
Well, just to be clear, we're going over how to do like the inverse Laplace transform now, right?
Yes, yes. Okay. Sorry, that's right. I guess it is called an inverse Laplace transform. My brain automatically went to inverse matrix since it was already there. Yeah, Carl. So the inverse Laplace transform, right? What is it? We're going to talk about it again in a minute, right? But the inverse Laplace transform is how we are going to take, once we take the Laplace transform and we manipulate our equation in the Laplace domain, we need to pull it out and pull it back into the time domain so that it makes physical sense based off of the responses that we have. And that process is the inverse Laplace transform. And we're going to talk specifically about how to do that today. We're going to talk specifically how to do that today. But first, let's have a note on the lab. First of all, I don't know how many of you have been on LoudCloud since last class, or really since yesterday, but last night I moved the due date of the lab back to Wednesday of next week. So instead of Sunday, you can turn it in on Wednesday. Okay. So that's the first note on the lab. All right. The due date has changed. Okay. Secondly, I want to talk to you guys about this, right? So there's a lot of different ways that we can develop a model here, right? And so one of the things I want to talk about, right, is what exactly, right? So we've got this, we've got these, I'm going to try my best to draw this as best as I can, right? It actually does not look like that at all, right? So I'm just going to draw it like this, and we've got these connected cars, right? And I've got something that's attached to a gear here, right? I know that's really accurate and highly representative of what we have. But what's going on, right? We apply some current to our motor spins, and then this, as this rotates, right? We'll just say it's rotating this way with some angular velocity, right? It's rotating this way. As this rotates, this arm is going to move back and forth, right? We'll use red. So we're not going to model the motor itself because we don't know how that circuit, we don't know the inductance, we don't know the resistance, right? We're not going to model, we could model this disc, right? And for that disc, I'll get you guys the radius of the gear, right, later today, after I actually measure it. But let's talk about what this motion looks like, right? So we've not done a problem like this, except that we've done a problem that looks like this one, right? Where I've got a spring and a damper, right? That's attached to a mass, right? And we said that instead of having a force, right, we had some input Z0, right? So I'm moving the floor. The floor can move, right? And the mass can move, right? We've done this. This was in a homework, right? So what if I turned it on its side and I said, you know what? Instead of me looking at this as if I have this crankshaft here and trying to determine what the torque input is, what if I already know what the input is, right? Because you would expect this to what, right? As this rotates, right? This is going to continuously rotate, right? This is going to rotate. So what's it going to look like? Well, let's zoom in on this disk, right? We're just going to look just at the disk. We're going to remove the bar, right? We're going to say there's some hole on the disk that's here. And this, we're going to call this point P for right now, right? And at point P, I've got my bar attached, right? This is my starting position, we'll say, right? As this rotates, point P will eventually make its way over to here. We'll call it P prime when it gets here, which is also going to have, which means the bar has shifted, right? So the entire distance that this has moved, we'll call this capital D. What is that distance? It's known as the stroke length, right? This is the maximum distance that this bar can travel, right? And it's the diameter of the circle that this point travels along, right? So if we started at point P and we say, well, that's 0, by the time we get to P prime, we're going to have moved by D. And then by the time we get to P again, we're back at our starting position, right? So we have a relative displacement of D here. Right, so let me draw this. What is this motion looking like, right? Because we want to know what the translational motion is. All right, so if I've got my X position here, and we'll say this is time on the X axis, right? And this is going to be in units of distance, right? Because I don't have any units on there yet. And this will be in units of time, typically seconds, right? So if I start at 0, and what's going to happen? Well, over time, I'll hit some point, then I'll come back to 0, then I'll hit some point, I'll come back to 0, forever. Well, that looks an awful lot like a sine wave, right? Looks an awful lot like a sine wave with the amplitude of that D, right? So if you ignore the motor, well, not ignore, right? We're not ignoring the motor. We're just not going to model the motor. right? Because I know what the output is supposed to be, right? The output is going to be this sine wave. Well, Dr. D, we don't know, right, what the period is, right? Because the period is going to tell me the frequency, right? Because right, isn't your frequency just 1 over the period, right? So you can take the motor and the rotational components, and you can say, well, I know that this is supposed to give me a sine wave. So how am I supposed to get omega, right? How am I supposed to get omega? Well, how are we supposed to get omega? Well, when you watch the video, right, turns out, and we'll learn about this in frequency response, a little bit of preview for this. But it turns out that if the system reaches steady state with a sine wave, the initial input velocity or the initial input frequency is the same as the final input frequency, right? If I apply a sine wave at 4 radians per second to a system, I will get out something at 4 radians per second, right? It's going to be a shifted sine wave, right? But it will still be running at that frequency, okay? So if you watch the video and you're watching how the third car moves, right, you can determine the frequency from your data points, right? Because you can determine the peak to peak time, which is your period. And then if you take the inverse of your period, 1 over your period, you will get the frequency, right? Right? So we get something like this, right? So what does this mean, right? If we're looking at this, this would mean that, let's call it x0, right? Let's call this x0. So this would mean that x0 would have to be a sine wave that had amplitude d sine of omega t, right? Sine of omega t. Okay. So we can model this as a sine wave that has an amplitude of my stroke length. Now, I'll measure these things. So what is, all right, so let's go back for a second to that previous picture though, right? Because, well, I'll just draw it again, right? So here we go, right? I've got mass 3 connected via my, and I'll actually draw it appropriately this time, right? I've got a spring and a damper here into mass 2 with a spring and a damper here into mass 1, right? This has some Z1, this has some Z2, and this has some Z3, right? These are all K and B, K and B. Our input here is X0, which is a sine wave. Now, why could we go all the way back and link I, like the current input all the way? Yes, we could, right? But it's not necessary, right? And it's a little bit more, it's a little trickier given the information that we have. So if you set up your model in this way, right, where you can pull everything that you need to know, right? And I'll give you that distance, right? Today after class, I'll measure it. I can find my, give me 1 second. I actually measure it there. Please hold. This is it. So D for our system, D is 0.5 inches, and R, the radius of our gear, is roughly 1.5 inches. Okay. Hopefully that helps clear some things up regarding the lab. Okay. You guys have any questions?
I might have been completely lost then, because yesterday I was looking at because you have your playlist for the fall semester, and you're talking about multiple carts, but like the only one I find is like your episode 2 of rotational electrical mechanical system lab. Is that the one you're referring to?
Yes.
Okay.
Yeah, that's the lab that you're working with. Episode 2 of Dr. D and Professor Price D lab. It's a highly rated YouTube series for sure. I did not know that I was viral. No, Kat, I did not know.
I guess I'm just trying to ask is like when you mean because you have 3 masses here, right? Are you just referring to like 3 masses wanted because you did 3 trials and like you added weight each time, or like because you keep on talking about 3 carts, but I only see like in the video like
Right.
1 cart moving with.
Carl, the only one in the video is mass 3, and that's the one I want you to model the whole system using, but I want you to output this position.
Oh, okay. I'm being so dumb.
The other 2 are still connected, and you still have to model it to figure out, right? Because there's a spring and a damper between them, you are going to be storing and dissipating energy at different rates, right? And so the Z values for each of them is not going to be the same, right? But the thing about the third cart is, right, so now you have D, how do we find omega? Well, by reading your data, right, and plotting it out kind of like this sine wave here, you can still get the peak to peak time, right, which is your period. And once you have the period, you have the frequency, because the frequency is immutable throughout the entire thing. The frequency stays the same, right, regardless of, because think about this, right? Frequency, we use omega, and we also use omega for angular velocity, right? And it's not a coincidence because those 2 things are really the same thing, okay? They even have the same units, right? Radians per second. Okay, so if you're given omega, you're given the frequency, right? If this is at steady state, it's going to be at a constant angular velocity, which is also my frequency. Okay. All right.
Okay, this makes so much more sense. I was so confused last night. But okay, thank you so much.
Yep. So question was, what are we excluding from the original model? You're not really excluding anything. You're just consolidating. So think of it this way, right? When we did the solenoid the first time, we treated it as just a mechanical model that we knew what the electromagnetic force was, right? So we knew the outcome of the electrical side, right? In this case, we know the outcome of the rotational piece, right? That rotational piece is going to cause this oscillatory input, right? This sine wave input. And so we're just saying, right? So how would the current change that, right? Well, if you don't have the same current, right? I think this is, if you think about how motors work, right? If you apply a current to a motor, the more current you give it to a certain point, the faster it will spin, right? So current and frequency are directly related in some way, right? We can do this, right? And you're going to have a different frequency likely for a couple of the trials, right? Because one of them's at 7 amps and the other 2 are at 6.5, right? So you're going to have to really make sure what your frequency is. Now, it'll probably be pretty close, but they're probably going to be slightly different. Okay. Any other questions? I'm sorry, say that one more time. So in the lab, it's not something that we are in fact going to do. Okay, so just go with the data sets that you have in the video, right? Create a model and test it for what you have in the video, and that's all you need to do. Okay, then compare, right? What I want you to compare, because I know in the video it also says something about predicting the current that you need. Don't do that. Compare, I want you to compare the model value that you get out for Z3 to what actually happened in the experiment. That's what I want. And you can compare the average values. That is fine. Don't feel like you need to get granular with it and use, period and comma to go frame by frame and get the exact position at every frame. Take the average position, right? You are going to need to figure out what the frequency is, but outside of that, just find the average position that the third mass moves, okay? Yes. Office hours tomorrow from 3 to 5. Today, I've got class until 5 p.m. It's a great day. Sure. Any other questions? All right, lab's due on Wednesday now. Okay? Lab's due on Wednesday now. See, I even changed it in the slide. That's how official it is. Right? I even changed it. That you guys know how hard it is for me to do these slides. This is a big deal. I can't use technology. PowerPoint. Anyway. All right, lab due on the 18th, homework still due on the 22nd, right? And then exam 2 on the 24th. Okay. Yeah, it's a crunch. I will likely push back lab 3 because lab 2 got pushed back, right? What's that? Yeah, I will post them on Monday morning, Sunday night. You'll get them. You will get them. I can't give them out before the homework's due. I mean, I could, but I think you guys know me well enough after 10 weeks. No, I'm not going to do that. All right. So are we good? Anybody have any other questions regarding lab, right? Otherwise, we've got some stuff to talk about today. And my plan for next week is if we can get through most of this, next week is going to be more like the first couple weeks of class where I'm going to post a set of example problems online for you guys to try. And then we will just kind of work through examples, right? If we can get through most of this stuff today, okay? That's the plan. Any other questions? All right. So what is an inverse Laplace transform? I know we went over some of this at the end of last class, but I thought it'd be good to just kind of go over it again, right? So what is the goal of all of this, right? So our overall goal is to use the Laplace transform to obtain the response of a dynamic system that's subjected to some initial conditions and or a known forcing or input function, right? So I want, the order of events is this. I want to take the Laplace transform of something. I want to mess around with it, solve it in the Laplace domain for a variable of interest, and then take the inverse Laplace transform to get it back into the time domain. Because like I said on Tuesday, right, Nightcrawler's powers work. He teleports himself into an alternate dimension, and then he pulls himself out, right? So we're useless if we can only do half of those things, right? We need to do the whole thing. So how? How do we do this? Well, I kind of told you guys. It's a systematic approach for solving ODEs, right? First, we take the Laplace transform of every term in our ordinary differential equation. Where does that come from? Well, that's our modeling equation, right? That's the whole point of the entire first you know, 3 topics in the class when we learn how to model things, right, is that we get ODEs out. So now that we have the ODEs, we take the Laplace transform of everything in it, right? Both sides, right? Input side and output side. Then using the results from that first step, we solve the Laplace transform for our output, right? In this case, it's in general, it's called y of s, but it doesn't have to be y of s, right? We can have other variables that are our output. And then we take the Laplace transform, right, of y of s, and that will get us back to y of t. Now, I haven't really shown you guys how any of this works. We've talked about it. So we're going to go through this example, right? So I've got this second order ordinary differential equation, right? It's got an initial condition of y of 0 of -1 and y dot of 0 of 0.5. And I want to determine the dynamic response if I have a step input of 4, right? So 4 times u of t. What is capital U of t? If we go back a few weeks, couple weeks to when we started this topic, when we started topic 4, time domain stuff, right? We said, we introduced input functions, right? And we said, well, this is 0 for time less than t and 1 for time greater than or equal to time of t, right? Right, what is time? Time is the time it turns on, right? We often say that that's at time 0. We're starting a step at time 0, but we've seen examples where we've used other times, right? We've seen examples where we've used other times. So it's a piecewise function. It's 0, right? Capital U is 0 before we turn it on and 1 afterwards. Now this one's getting multiplied by 4, right? Because it's not a unit step. It's 4 times the unit step, which is a step of 4, okay? So what do we do? Well, based off of the previous slide, right, I'm going to take the Laplace transform of this entire equation. Right, and remember, Laplace transform is a linear operator. And because it's linear, I can distribute the Laplace transform to each of my terms here, right? So this is the same as taking the Laplace transform of 2y double dot. Right, so let's take the Laplace transform of 2y double dot. Why don't we? Now remember, last class there were a few properties that I put a box around, right? They're also, right, the differentiation properties, right? They're also on the master sheet, in case you forget. It's written in the most general form. This is a second order derivative. For a second order derivative, hold on, let me get to the right part of my notes. Right. Well, I can pull the constant out, right? We've talked about this. If you have the Laplace transform of a function, the times a constant, the constant can come out, right? Why? Remember, because what is the definition? The definition of a Laplace transform is that you're taking the integral from 0 to infinity, right? So this 2 pops out. So we're left with 2 times the Laplace transform of y double dot. And the Laplace transform of y double dot is s squared times y of s minus s times y of 0 minus y dot of 0. That is the Laplace transform. So what is y of s? Well, y of s is the Laplace transform of y of t. Seems unhelpful right now, right? It does. But it's not unhelpful because you have to remember that's what we're trying to solve for, right? Because what the Laplace transform allows us to do is take this ordinary differential equation and then manipulate it using algebra, okay? So once I get the Laplace transform of all of my terms, I can rearrange it using algebra. I can group all of my like terms together, and I can solve it for y of s, right? Because what's going to happen? I'm eventually going to take the inverse Laplace transform of y of s to find out what y of t is, okay? So this is just using the derivative property for a second order derivative, right? And we can plug some things in here, and we can distribute our 2 times through there, right? So y of 0 was -1, so this is going to be plus 2 times s, right? Because y of 0 is -1 minus s times -1 right, is just plus s. Then we multiply our 2 through the entire thing. Right, minus 0.5 times 2 minus 1. So eventually, right, this will go. We'll rewrite the equation with that term there. Okay? Eventually. Well, we're going to keep going, right? Because then I've also got to take L of 10 y dot, right? And L of 10 y dot, well, again, right? I can pull the constant out. And what is the Laplace transform of the first derivative? We can pull that off of our master sheet when we're taking derivatives of when we're taking the Laplace transform of the derivative of a function. This is s times y of s minus y of 0. Okay. Which we can also rewrite because, right, this just becomes 10s y of s plus 10. Right, because remember, y of 0 is -1 minus -1 is +1 times 10 because the whole thing gets multiplied by 10. This one's going to end up going here when we rewrite our equation, right? We're going to take the Laplace transform of 2 more things here, right? 2 more things. We'll talk about it in a minute. We'll do the other left-hand side one there, right? Laplace transform of 12 times y. Well, the 12 comes out, and the Laplace transform of y of t is just y of s. And again, remember, we're trying to solve this entire thing for y of s at the end of the day, right? This goes right in there. Okay. So we've got the whole left-hand side. Now we have to take the Laplace transform of our input. Now we have to take the Laplace transform of our input. Is everybody okay so far with what's happened here? If you look at the master sheets, let me pull up mine. If you look at the master sheets, this, right, on page 4 of the master sheets, is that right? I don't know. Under Laplace transforms, the second one is differentiation, right? And differentiation gives us this, L of d to the n dt n times f of t, right? Well, f of t for us was just y. Right? Well, in our case, our highest order derivative, right, was 2. So if we go by this, we'd have s to the n, which is 2, times f of s, minus s to the 1 times the initial condition, f of 0, like lowercase f of 0, minus, well, now s to the 0, right? F prime, f dot of 0. Right? So you basically just keep throwing s's in there, right, until they go away, until you get the s to the 0. Okay? That's where this comes from. And you guys, right, that's the most general form is given to you on the master sheet, right here. Okay, so we've got this here, right? Now what? Now we've got to take the Laplace transform of u of t, right? So let's do that. So the Laplace transform of u of t. Well, this, we know what u of t is, right? We were told that u of t is 4 times u of t, capital U of t, right? And capital U of t is 0 for part of it and then 1 for the rest. So when it's 0, right, the Laplace transform of 0 is 0, right? Because remember, the Laplace transform of a constant is a over s, right? And so 0 over s would just be 0. So we really are only concerned about this once the step input turns on, right? And when it turns on, it just becomes the Laplace transform of 4. Well, from the table, right, it's just going to be 4 over s. So why isn't it u of s, right? Well, it's not u of s because, all right, so it's not u of s because we know what u of t is, right? We know that we have a value for it. We have a value for our input, so we have to take the Laplace transform of that value. Another way of thinking about this, which might confuse everybody, right, is we're taking 4 of capital U of t, right? I can pull the 4 out, and if you take the Laplace transform of this piecewise function, it just equals 1, right? So you get 4 times 1 over s, right? Same deal, same deal. If you have a step input, right? This one comes up a lot. This one comes up a lot. And I will never tell you to memorize anything, but this one comes up so often that you're just going to end up knowing it after a bit, right? Because we use it all the time. Step input is an extremely common input. Extremely. So it's just the magnitude of my step divided by s. That is the Laplace transform, right? And so now I have everything, and I'm going to rewrite my equation in terms of my Laplace transform variables, right? So we started with, let's see, Laplace transform of 2y double dot, and we got that that was 2s squared times y of s plus 2s minus 1. Right, the next part, the Laplace transform of 10y dot plus 10 s y of s plus 10, and then the Laplace transform of 12y, and that all equals 4 over s. Okay, and that's where we're at. And I think that's where we, that's basically where we stopped on Tuesday, right? Okay, so now that we're here, we are going to algebra this, right? And I'm going to group all of my y terms together, right? And I'm going to move everything else that's not a y term to the other side of the equation. Okay, so I'll group all my y's. So I've got 2s squared plus 10s plus 12 times y of s is equal to 4 over s minus 2s, right? Because that's my only other s term, right? 2s. And then I've got negative 1, right? So this is what I'm looking at. I've got negative 1 plus 10. So that's going to be minus 9. Part on the left kind of looks like the characteristic equation, doesn't it? Doesn't it? It does. Okay, so I'm going to do a little bit more algebra here, right? And I'm going to put a common denominator of s on the right-hand side, right? So I want all of this over one single thing, because then when I divide out my 2s squared plus 10s plus 12, it gets messy otherwise, right? So I'm going to create a common denominator to start with, right? In doing so, you'll get that this is equal to 4 minus 2s squared minus 9s over s. How did he do it? Well, I just multiplied my other two terms by S over S, which is legal, right? Because S over S is 1. So I've not changed the value of any of those terms. All I've done is multiplied by 1. But I did it in a cool way that made, that made it useful. So now we can divide through, and I'll get 4 minus 2s squared minus 9s over s times 2s squared plus 10s plus 12. There we have it, right? We can inverse Laplace transform this now, right? We can inverse Laplace transform this now. So we go to the table and we look at it and we're like, Dr. D, this specific Laplace transform is not in the table, right? Because if it was like 1 over s plus 3, we would go to the table, we'd be like, man, this looks like e to the negative at, right? So I'll grab that, this is e to the negative 3t. Inverse Laplace transform complete. But that doesn't work for us here, because there's nothing on the Laplace transform table that looks exactly like this, right? And we need it to look exactly like this, or we can't do anything. We can't inverse Laplace it by the tables. So what do we have to do, right? And I told you guys that we were going to do this. We'll go to the next slide. We are going to use partial fractions to do this. Now I want you to think about this for a second. If you were doing this in the time domain, right, I would tell you that the first step is to check the roots, right? That's what I would tell you. Why? Because the roots tell us what kind of responses we're supposed to expect to get out, right? We did a whole class where we talked about the different root responses. There was a question on the homework that talks about the root responses. The root responses must be important because it keeps saying root responses, right? So we're going to do this, we can do the same thing here, right? So what I'm going to do is I'm going to take my function, right, to do partial fractions, right? We solved for y of s, and I've got 4 minus 2s squared minus 9 over s times 2s squared plus 10s plus 2. Right, that's a 2. And I can factor the bottom. I'll factor my denominator. And I'll get s times, I'm sorry, I will pull, well, let's do this. Right, and so I will pull a 2s, and I'm going to pull a 2 out over here. Right, so I'm taking 2, right, this 2. I'm dividing, I'm just pulling 2 out from all of these terms, right? Because why? Because there's a 2 in all of those terms. That's why. Right, so that's going to be s squared plus 5s plus 1 instead on the inside. And if I factor s squared plus 5s plus 1, I'll get s plus 2 and s plus 3.
Hey, Dr. D.
Should be 12. Sorry, I can't read my writing. My bad. Good catch. Was that what you're going to?
I was going to say, was the 9 supposed to have an S as well?
Yeah, man. Dang. It's going to be that kind of day. Jeez. All right. So we've got our thing now, for real. All right, so all I did was I factored a 2 out before I took my roots, right? That's all I did. Not okay. So I've got 3 roots. Right, so I've got 3 roots here. All right, they're going to be 0, -2, and -3. Right, that hopefully that's pretty obvious how I got those. If it's not, you set each of those 3 terms equal to 0, and you solve for s, and you find out what s is, right? So 0, -2, and -3. Okay. So by partial fractions, right? we can split this into these three different root responses, because remember, in a linear system, we have superposition, right? And if we were doing the differential equations, we would look at all these roots, and then we would add up the responses due to these roots, right? So we're actually going to split this up based off of the different poles that we have. And I'm going to use these constants at the top. Right, so I've split this fraction into three separate fractions, each one of which houses the response due to one of my roots. Bless you. So what do we do now? Well, now you multiply through, right? Because if this is in fact true, where these two things are equal, right? I'm going to multiply through by 2s, right, by the denominator of the fraction on the left. Okay? So let's do that. Let's multiply everything by 2s times s plus 2 times s plus 3. And if I do that, right, I'm left with, well, all right, before we do that, I'm going to divide by 2 on this one, right? So I've got, all right, so if I divide everything here by 2, right, to get rid of this term that's in front, that's what I'm going to do. So let me rewrite that out so that we can all, right, so it's 2 minus s squared minus 4.5s over s times s plus 2 times s plus 3. Do you have to do that to start with? No. You could keep the 2 there and multiply through by everything. That's fine. It's just, I just like to do that, right? And this is equal to a over s plus b over s plus 2 plus c over s plus 3. It's going to be a little cleaner. It's going to be a little cleaner because once I'm going to multiply through by this denominator now, right? So let me show this, right? We will multiply both sides. I'm not going to have enough room to write it on the one side, right? But, all right, so I'm multiplying both sides by this term. I'll just write, I'll write it in red just so we have a denominator, right? I'm multiplying by the denominator here. I just don't have enough room to write the whole thing. Right? So if I multiply through by s times s plus 2 times s plus 3, right? This and this will cancel. Yeah? So I'm going to be left with 2 minus s squared minus 4.5s. And that's going to be equal, well, if I multiply a over s times s plus 2 times s plus 3, I just end up with a times s plus 2 times s plus 3, right? Because the s's cancel. And then for b, I end up with b times s plus 3 because the s plus 2's will cancel. And then for c, I get c times s plus 2 because the s plus 3's cancel. All right, so cool. We ended up with 3 real distinct roots in this one, right? We ended up with 3 real distinct roots in this problem. And we have 3 distinct portions of our solution. Okay? So now we just need to solve for A, B, and C. So how do we solve for A, B, and C? Well, first, I'm going to algebra a little bit more, right? I'm going to expand all of my terms. Right? So I'm just expanding all of my terms. And there's a distinct reason why I want to do this, right? Because I am going to say that all of the s squared terms, the coefficients of all the s squared terms, have to equal the coefficient of the s squared term on the left. Right, so give you a second to copy it down. I'm going to rewrite this on the next slide just so we have it, so that there's enough room. Well, apparently there is no next slide. Let's change that. Let's get a next slide in there. We'll add two just in case. All right. So what did we have, right? We had 2 minus s squared minus 4.5 s is equal to as squared plus 5s, 5as plus 6a plus bs squared plus 3bs plus cs squared plus 2cs. That's what we ended up with. Well, that's what we ended up. So I'm going to take my s squared terms, right? I'm going to say, well, on the left-hand side, I've got -1 as the coefficient to my s squared term, right? And that has to equal a plus b plus c. So let me do it this way. Let me do it this way. Right? I'm going to underline all of my s squared terms in red. I've got -1 is equal to a plus b plus c. All of my s terms get underlined in green. S to the 1 term. Right? That's s to the 1. What do I get? Well, I've got -4.5 is equal to 5a plus 3b plus 2 times c. And my s to the 0 term, right, we'll underline those in blue. Oh, hey. 2 is equal to 6 times a. S to the 0 is just 1, right? S to the 0 is just 1. And look at that. I've got a system of 3 equations with 3 unknowns. So I'll solve those, right? Use your favorite method, right? My favorite method is to put it in my calculator and let my calculator do it for me. But you don't have to do that, right? You could solve for a directly, right? We can all see, hopefully, that a should be equal to 2 over 6, or 1/3, right? From that third equation. So a is equal to 1/3, right? Then if you take a and you plug it into the other 2 equations, you can solve those 2 simultaneously, right? So you plug a into the other 2 equations, you solve one of them for b, plug that into the other equation, solve for c, take c, plug it back into the other equation, solve for d, right? So we're left with this. So I want you to remember what we started with, right? We started with y of s was equal to some function, right, that had, well, we started with 2s squared, 4 minus 2s squared minus 9s over s times 2s squared plus 10s plus 12, right? That's what we started with. And we said that all of that had to equal a over s plus b over s plus 2 plus c over s plus 3, right? That's what we said. That's what we said. So y of s equals a over s plus b over s plus 2 plus c over s plus 3, right? But I know now, after solving this, that this is just 1 over 3 times 1 over s, right? This is a. A is 1/3. 1/3 over s, right? Or 1/3 over 1/3 times 1 over s, right? Well, B was negative 3.5 over S plus 2, and C was 2.17 over S plus 3. Take a look at that. Now those are things that I can now take to the Laplace transform table. Right? I'm going to rewrite this on the next slide so we have some room. Y of S is equal to 1/3 times 1 over S minus 3.5 over S plus 2 plus 2.17 over S plus 3. That'll shift up. Maybe not. There we go. Okay. So now I'm ready. I go to my Laplace transform table, right? What's 1 over S in the Laplace transform table?
One over S is just 1.
Right, yeah. It's just a step, right? So 1/3 times 1, we're up with a third. What does the next one look like? Negative 3.5 over S plus 2. What should I have here? Are there any Laplace transforms that take the form of something over S plus a constant? Yeah, it's e to the negative at, right? So negative 3.5 times e to the negative 2t. What about the next one? What should the last one be? Yep. That's the answer. That is the time domain response for our equation. No, I mean, yeah. So Kat's question, right? Do you have to, I mean, indicate in some way that you've taken the Laplace inverse, right? I did it that way so it would be obvious and apparent that we took the Laplace inverse, right? If you just, in your notes, right, if you wrote like Laplace inverse of y of s, right? But the process is this, right? We do partial fraction expansion based off of what the roots are, okay? We do partial fraction expansion. And once we solve that, now we've got our equation in a format that is usable in the Laplace transform table. Now, isn't it, no, I mean, were you expecting this result? And the answer should be yes, because you knew what the root response was, right? Because you checked for the roots originally, you knew that you had something that's marginally stable, right? Something that had a root at 0, right? That's where the 1/3 comes from. You've got something, and you've got 2 exponential decays, right? And how do you know that? Well, because you've got 2 negative roots. So this result makes complete sense based on what we know from differential equations, right? The utility of the Laplace transform and inverse Laplace transform seems trivial for something like this when we know exactly what the root response is and how it's supposed to behave. But for extremely complex systems, right, where we've got lots and lots going on, this is something that is extremely useful because, you know, higher order systems, rather than having to solve it using differential equations, we can do some algebra to get the answer. You can even check this with the initial conditions to see if it pans out. So if you plug in y of 0 here, what do we get? So what is that? What do we end up with? -1, right? Which checks with our initial conditions, and it should. Right? 100% should check with it because we used our initial conditions to create this, right? And if you took the derivative of that function and then plugged in y dot of 0, you would get back out 0.5. You guys have any questions? Is partial fractions something that we've seen before? Yes, right?
Yes, we've seen partial fractions before.
Say that one more time, Adrian.
Yes.
I was saying yes, we've seen partial fractions before.
So the initial condition, you mean for U of t? For U of t, capital U of t is a piecewise function, right? That's our unit step. And so we're saying that when it's 0, right, that means there's no input to our system. And if there's no input to our system, then the Laplace transform of 0 is just 0, right? But for any time greater than or equal to the time that we've applied it, it will be equal to 1. So that's not an initial condition. That's just the definition of what the unit step is, right? Because remember, we can break down any step function into unit step times an amplitude. I'm sorry, I think I missed the question from you guys on the Zoom. Somebody have a question? No? I imagined it. Oh, okay. Gotcha. So let's talk a little bit more about partial fraction extension, right? Because there's a couple rules that we need to cover, we need to follow, right? So partial fraction expansion is the key to the previous example, right? That is, it unlocks it, right? It's what allows us to eventually get to a place where we are comfortable using the Laplace table to bring something out, right? For distinct poles, which is the example that we had before, right? Distinct real roots, distinct poles, right? We get something that looks like this, where y of s is equal to a1 over s plus the pole, right? We had 0 at 1, right? So that was just s plus 0, which is s. Okay? So this is the general definition of how partial fractions work, right? And then we can evaluate each of the residues, right? So what is a residue? Well, residue, right? Each one of these will have a residue. AI is equal to s plus p times y of s, where s is equal to negative p. Now that's the technical way of doing it, and we'll calculate one with residues in a second to kind of highlight how to do residues. But I personally don't like using residues. That is not how I do it. You guys saw how I did it, right? I take the whole thing, I write out my fraction, I multiply both sides by the denominator, I get one equation, I set all of my coefficients with my s squareds equal to each other, all of my coefficients for my s to the 1s equal to each other, right, and so on. But if you wanted to use residues, that's fine too. What is a residue going to give you? Right? Residue, right, is just this, just these numbers, right? That's going to give you A, B, and C. It's the same thing. The same thing. Both are equivalent. So let's compute the Laplace transform of this one. We're going to compute the Laplace transform. And this one, I'll do it both ways, right? I'll do it with residues and I'll do it the way that I just did it on the previous slide. You guys will see that these things end up being equivalent, right? The textbook talks about residues, so that's why I've talked about this, right? So I'm going to take this, right? And I'm going to leave 2s plus 5 on the top, but I'm going to factor my denominator here, right? And if you factor it, you end up with s plus 2 times s plus 6. Which means what, right? Which means we have poles at -2 and -6, right? So great. Distinct real roots, right? Distinct real poles. So we're going to do this the way that we've been doing it, or that we just did the last one, right? Which gives me A over S plus 2 plus B over S plus 6. Right? One constant per root, right? One constant per root. If I multiply through, right? So I'll take this, right? I'm going to use the red now, and I'm going to multiply everything times s plus 2 times s plus 6. Right? I'm going to multiply this entire thing, both sides. And if I do that, the left-hand side reduces to 2s plus 5, right? Because multiplying by s plus 2 over s plus 6 cancels the denominator. And that's going to give me a s plus 6a, right? I've just distributed, right? A times s plus 6 because the s plus 2's cancel. So a times s plus 6 is just as plus 6a plus b s plus 2b. Well, everybody cool? Everybody with me so far sees what I'm doing? Yeah. All right. I'll take my green terms, right? My s to the 1 terms. This is 2 is equal to a plus b. I'll take my blue terms, or my s to the 0 terms, and say that 5 is equal to 6a plus 2b. I will solve both of these simultaneously using my favorite method. Solve simultaneously. And I'll get a is 1/4 and b is 7/4. Let's check. 2 is equal to 1/4 plus 7/4. Yeah, that's 8/4. 8/4 is equal to 2. We're good. Right, so that gets me A and B. And A and B are my residues, right? And if I got this far, right, what do? Well, last problem, what we did was we plugged in A for A and plugged in B for B, right? So you get 1/4 over S plus 2 plus 7/4 over S plus 6, right? We go back to the Laplace transform table. So Y of S is equal to 1/4 times S 1/4 times 1 over S plus 2 plus 7/4 well, 1 over s plus 6. So if I take, well, I'll just write it underneath here. So by the inverse Laplace transform of this, y of t is what? Using the Laplace transform, what should I have as my inverse? What should I be pulling out?
It should be 1/4 times e to the negative 2t plus 7/4 times e to the negative 6t.
Nice, Carl. Thank you. Good stuff. Let me see something. I don't have another slide. I have to grab one. Oh, hold on. Okay, so we're there, right? So let's try it with the residues method and see if that is equivalent. So if I wanted to use residues instead, right? Like the textbook talks about residues. Well, the residues tell me that A1 is equal to S plus 2, right? S plus P1 times Y of S evaluated at S is equal to negative 2. Okay. Okay. So this tells me, well, Y of S times S plus 2, right? So this is going to be S plus 2 times Y of S. Y of S was 2S plus 5 over S plus 2 times S plus 6, right? So these go away, right? And I have to evaluate this at S is equal to negative 2. So if I do that, right, I get negative 4 plus 5. Right? So evaluating it at S is equal to negative 2. Just plug in this, right? So negative 2 times 2 is negative 4 plus, that's 1 over negative 2 plus 6 is 1/4. Okay. We can do it again. A2 is equal to S plus 6 times Y of S. Evaluated at S is equal to negative 6. So that's S plus 6 times 2S plus 5 over S plus 2 times S plus 6. S plus 6's cancel. We evaluate that at negative 6. That's negative 12 plus 5, which is negative 7. And negative 6 plus 2, which is negative 4. Well, the negatives cancel, and you're left with 7/4. Right? So you can get the residues, and the residues will give you A and B. Right? Same thing. Then you make a judgment on what it's supposed to look like, right? The reason I like to do it the way that I do it is because you end up with a function that is very clearly and easily able to go back into the Laplace transform, right? The Laplace transform table to pull out my inverse. Okay. Okay. We have any questions on real and distinct roots for Laplace for partial fraction extension? Is everybody all right so far? Any questions? Yeah. Mm-hmm. Mm-hmm. Yeah. So that 2s plus 5, right, is, remember, we're making everything equivalent to, all right, so if we start off the way that we've done this, right, we factor our denominator, right? Then I multiply everything by the denominator and get rid of it. So I'm left with 2s plus 5 is equal to as plus 6a plus bs plus 2b. That equation is telling us, based off of this root response, or based off of my input, which is approximately 2s plus 5 in some way, right? Based off of that input, these are the values that I need to associate with my roots, right? This is how I'm modifying my root. And so we can split up all of my s to the 1 terms, right? And we set those equal to one another. We split off all of the s to the 0 terms. So that 2 and that 5 are taken into account in A and B and how they affect A and B combined, right? Does that make sense? Right. Hey, you can do this in MATLAB. MATLAB command residue. What do you give it? You give it the numerator, right? The coefficients of your numerator, give it the coefficients of your denominator. If you set it equal to APK, right, then you'll get A being the residues, P being your poles, and K being your system gain. Well, I thought I had an example there, but I don't. Oh, got it. All right, so you can use this to get the residues, right? So if you did a partial fraction expansion by hand and you wanted to check it, you could get it this way. Right? You can check it in MATLAB. So there's two other cases we need to talk about, right? We need to talk about repeated roots and we need to talk about complex roots, right? Repeated roots and complex roots, and how do we deal with those? We're not going to talk about how to deal with purely imaginary roots today. Is not what we're going to talk about, right? So what do I've got? Imagine for a second this. I have this system. All right. Now 2s plus 8, right? I've already taken the Laplace transform. This is what I get. I get this third order system, right? And if I factor it, oh man, I get s plus 2 times s plus 2 times s plus 2. So I've got repeated roots. That seems, right? So all right, so just a over s plus 2 plus b over s plus 2 plus c over s plus 3, right? No. No, no, no. So how do we handle this when we have two repeated roots? Our partial fraction expansion looks like this. So we get a over s plus 2 squared, right? So we need to take into account both of the roots together. Then plus b over s plus 2, just one of the roots by itself, plus c over s plus 3. So we can do an inverse Laplace transform for this, right? Got ahead in my notes here. So if you take the inverse Laplace transform of this, right? Right, we didn't go through to find out what the residues were, right? We didn't do any of that. But just in general, if you can separate it out like this, right, you can know that you get something that looks like this, right? So if you go to the Laplace transform table, 1 over s plus 2 squared gives you t times e right, to the negative AT. So again, the idea here is that we will get our partial fractions. They will all be, we'll be able to break them down because it's a linear system, right? The combined response of our system has to be the addition of all of the root responses together, right? And so we can do this, right? The process is the same every time. The process is always the same, right? We take the Laplace transform of our function. We get our partial fraction expansion, right? Based off of what the roots are. We solve for A, B, and C, or A and B, right? However many we have to solve for. And then we look at it, we say, that looks like this version of my Laplace transform, right? And remember, it has to match exactly. Otherwise, you can't use it, right? You can also do residues. And residues for repeated roots are defined slightly differently. Right? So A1 is S plus 2 squared times Y of S, right? That one looks fine. But for the repeated root, you have to take the derivative with respect to S of the first equation. Okay. No. No, okay. I don't want you to solve it both ways. I want you to solve it whatever way makes most sense to you. That is the only reason, honestly, the only reason that I'm even talking about how to do this with residues is because it's in the textbook, and you know, at 11 o'clock at night, you're not going to be able to get in touch with me, but you are going to be able to get in touch with your textbook. Okay. That's what we're working with. Okay. Right, so if you solve the residues, right, and you can do residues in MATLAB too, right, which is, this is what MATLAB does when it, so if you use the residues command, it will give you A1, A2, A3, and you can check it. All right, any questions on partial fractions with repeated roots? We're doing all right. I think we're doing all right on time too, maybe. We'll see. Nothing? Yeah. Why indeed? Because A1 and A2 are both going to change in the same way with respect to one another. So in one, you're tracking what's actually happened because of both roots, and the other one, you're tracking the change due to those roots in the S point. Let's watch a video.
Everyone, welcome back. So today we're going to take a look at a problem with partial fractions, and specifically how to use these partial fractions to compute Laplace inverses. So just as a warm-up, we're asked to recall what the formula is for the Laplace transform of f prime in terms of the Laplace transform of f. In the second part, we're asked to find the inverse Laplace transform for three different functions. The first one is 1 over s squared minus 4, s squared divided by s squared plus 4, e to the minus 5s divided by s squared minus 4. And notice how we don't have any of these formulas, or sorry, none of these functions appear in the lookup table for a Laplace transform. So in each case, we have to use partial fractions to convert it or massage these functions into something which we do know the Laplace transform inverse for. And then lastly, for the third problem, we're asked to write down the partial fraction decomposition of this function 1 over s squared times s squared plus 4 times s plus 1 times s plus 3. And specifically, when we do the partial fraction decomposition, we're just going to leave the coefficients, the undetermined coefficients unknown. We're not actually going to solve for them. Okay, so I'll let you think about this problem, and I'll be back in a moment. Hi everyone, welcome back. Okay, so for part one, we're just asked to recall the Laplace transform of f prime in terms of the Laplace transform of f. So the Laplace transform of f prime we can write down as s times the Laplace transform of f, which I'll use capital F, minus f evaluated at the lower bound of the Laplace transform integral, which in this case is just 0 minus. Okay, so this is just part one. This is a warm-up problem. For part two, we're asked to find the inverse Laplace transform for three different functions. The first one is 1 over s squared minus 4. And we see here that we can factor the denominator into 1 over s minus 2 times 1 over s plus 2, which means that we can use a partial fraction decomposition, which has the form of a times, or divided by s minus 2, plus b divided by s plus 2. And now we need to solve for the coefficients a and b. So one way to solve for the coefficients a and b is just to multiply both sides of this equation through by the factors s minus 2 and s plus 2. We can then plug in values of s and solve for a and b. There's another way, which is sometimes referred to as a cover-up method. And in this case, what we do is we pick, for example, say one of the places where the denominator blows up. So for example, if we look at this factor s minus 2, this factor diverges when s approaches 2. So then what we do is we go back to our original function, we cover up the term s minus 2 where it diverges, and then in the remaining term, we plug in the value of s, which causes the factor s minus 2 to diverge. So in this case, s minus 2 diverges at 2, so we would cover this factor up and then plug in s is equal to 2. And this would give us the value of a. So for this problem, a is equal to 1 over 2 plus 2, which is just 1 over 4. For b, we look at plugging in s equals negative 2, so we cover up the factor that diverges in the original function. Plugging in s equals negative 2 gives me negative 2 minus negative 2, so b is just negative 4. So this function is 1/4, 1 over s minus 2, minus 1/4, 1 over s plus 2. And when we take the inverse Laplace transform, so the inverse Laplace transform of 1 over s squared minus 4 is going to be 1 over 4. The inverse Laplace transform of s minus 2 is e to the negative 2t plus 2t. The second factor is negative 1/4 e to the negative 2t. And this concludes the first problem. For the second function, we have s squared divided by s squared plus 4. So again, this function is not in the correct form to use a Laplace transform lookup table. But what we can do is we can divide long division of polynomials, the numerator out by the denominator. So when we do that, we end up with 1 minus 4 divided by s squared plus 4. So when we take the inverse Laplace transform of s squared divided by s squared plus 4, we're left with the inverse Laplace transform of 1 minus the inverse Laplace transform of 4 divided by s squared plus 4. And if we use our lookup table, we know that the inverse Laplace transform of 1 is the delta function. Meanwhile, the inverse Laplace transform of some number divided by s squared plus 4 looks like sine of, in this case, sine of 2t. Now, we needed 2 upstairs, so this is going to give us 2 times sine of 2t. And I obtain this by noting that the Laplace transform of sine omega t is equal to omega divided by s squared plus omega squared. So that's how I went from this formula, or this function, this Laplace transform inverse, to 2 sine 2t. Lastly, for part 3, the third problem, we're asked for the inverse Laplace transform of e to the minus 5s divided by s squared minus 4. Now note that we already know the inverse Laplace transform to 1 over s squared minus 4. In this case, it's just we're just multiplying 1 over s squared minus 4 by minus 5s. So we can use the shift formula in addition to what we already computed, the inverse Laplace transform to 1 over s squared minus 4, to compute this inverse Laplace transform. So the shift formula says that we need to multiply by the step function t minus 5. So we're shifting with the step function. And then what we do is we want to shift the inverse Laplace transform of 1 over s squared minus 4. So the inverse Laplace transform to 1 over s squared minus 4 is 2t minus 5. So if we shift t by 5, we end up with 1/4 e to the 2t minus 5 minus 1/4 e to the minus 2 t minus 5. So again, just to reiterate, when we have an exponential e to the minus, say, 5t or 5s, and we already know the inverse Laplace transform of everything else, we just multiply by the step function u, t minus 5, the same shift, and then wherever we see the t in the inverse Laplace transform, we just replace it with t minus 5 in this case. Okay, and now lastly, for part 3, we're just asked to write down the decomposition for this very large function, the partial fraction decomposition of this large function. So it's s squared times s squared plus 1 times s plus 1 times s plus 3. Let me just double check. S squared plus 4. Okay. And unfortunately, this function's going to be a little ugly. We're going to have a constant a divided by s plus b divided by s squared. So these first two terms come from this term right here. For the s squared plus 4 term, we're going to seek a c times s plus d. So we need both factors, cs plus d, divided by s squared plus 4. We have e divided by s plus 1, and then plus f divided by s plus 3. So just to associate each factor, or each factor in the partial fraction decomposition with the original function, I've just drawn some arrows. Okay, and then lastly, although I didn't state this in the original problem, we can also just write down the inverse Laplace transform of this entire mess. Without actually determining the constants, we can just keep the constants in. So if we wanted to compute the inverse Laplace transform, well, it would just be a, because the inverse Laplace transform of 1 over s is 1, plus b, inverse Laplace transform of s squared is t, plus, now this part has two terms, cs divided by s squared plus 4, that's going to give us c times cosine of 2t. The d divided by s squared plus 4 is going to give us Well, we need to multiply upstairs by 2 and divide by downstairs by 2. So we get d divided by 2 of sine 2t. This term e is going to give us e times the exponential of t, negative t. And then f is going to give us, or the last term is going to give us s, f times e to the minus 3t. Okay, so just as a quick wrap up, in this problem we've computed partial.
No, we're good. We don't need to wrap up. Thank you. All right. So, right, review of partial fractions. Now we're going to start talking about partial fraction expansion with complex roots. And he did one in that video, right? And the way that we treat complex roots is the same way that we treat purely imaginary roots, okay? So these are both going to be equivalent. So we're going to watch this video real quick. Try to lead into imaginary roots.
This screencast will show how to solve equations in the Laplace domain, or the S domain, which contain imaginary roots, and allow us to put them back into the time domain. To accomplish this, we'll use the equation shown on the screen here. To show the fact that this system in fact has imaginary roots, all we have to do is recognize the s squared plus 4s plus 5 part and realize that using the quadratic equation, if we look at the square root term of the quadratic equation, if this term is less than 0, that will tell us the fact that our roots are in fact imaginary. So when we do this, we have negative 4. So therefore what this shows is the fact that we have 2 imaginary roots. Processes which have imaginary roots are systems or processes which will oscillate in nature. From a mathematical standpoint, that represents the appearance of cosines and sines in our final solution. There are some processes such as swings and pendulums which naturally have this. However, most chemical processes do not have imaginary roots. Where we sometimes see the presence of imaginary roots in chemical process control is for some systems which are controlled using PID control, where it is possible to end up with imaginary roots. In fact, many tuning parameters take advantage of this fact and are tuned to ensure the fact that the process obeys quarter decay, which is an oscillatory response. Recall that systems with imaginary roots will have the form of a plus or minus I. But the question now becomes is when we're trying to convert this from the Laplace domain to the time domain, what functional form should we have? And the best way to answer this question is to look at the Laplace transforms that are available. Looking at the transforms provided here, what you'll see is the fact that there are no I terms here, and the fact that everything is left in s squared plus omega squared, or s plus b squared plus omega squared. So therefore, we don't want to solve these using the value I, which is equal to the square root of -1. So our focus here will be to leave things in s squared plus 4s plus 5 terms. In other words, our focus is going to be looking at the last two equations I've shown here in order to eventually take the inverse Laplace transform. To do this, what we're going to have to do is use partial fractions. So what we'll do here is just rewrite what we have above and then break it into its roots. And what we'll have here is a over s, but we don't want to break the other root because of the fact that we don't want to deal with i's, because the i's provide us no help in trying to use the Laplace transform table. But what this means is that the numerator of this will not just be a constant, but it'll be of the functional form bs plus c. To solve for a, b, and c, our focus will shift to the numerator. What we'll now do is find a least common factor and multiply the a by the s squared plus 4s plus 5 and the bs plus c term by s, of which this must equal the numerator we already have, 3s squared plus 5s plus 5. We'll provide that here. What you'll notice on the right-hand side is that the highest power of s that we have is s squared. So what we now want to do is break this down into terms with varying powers of s, and we have 3 of them here. We have s squared, we have s to the first, and we have s to the 0. In other words, the constant terms. So if we look at our right-hand side, we see that we have an as squared term and a bs squared term. If we look at our s terms, we have 1 for a, 4as, and we have 1 for c, c times s. For constant, the only one we have is 5a. We then use the left-hand side to match what these coefficients have to equal. So if we look on the left-hand side, we have 3s squared, 5s, and 5. We can now solve for a, b, and c. First, we'll start with the s to the 0th equation to find a. a equals 1. We can then substitute in a equals 1 to the s to the first term, and that will show that c also equals 1. And the s squared equation will allow us to solve for b. b equals 2. Now that we have solved for all of these constants, we can substitute them back into the equation shown above. When that substitution is done, the equation is the one shown here. The inverse Laplace transform for 1 over s is relatively straightforward. It's just the inverse of a step function, which is just a constant. That's 1. In order to take the inverse Laplace transform of the second term, we have to go back to our Laplace transform sheet. As noted before, our focus here will shift on the bottom 2 equations because we don't have a perfect s squared plus omega squared in our denominator. But what we now need to do is find b and omega. In order to do that, we have to complete the square of the denominator. So in order to complete the square, s squared plus 4s plus 5, in order to complete that square, what you do is you take half of the value for the s term, which is 4, and then take the square of it. So therefore that would be s squared plus 4s plus 4. You then add or subtract whatever the difference is with the original constant you had. So therefore originally we had a constant value of 5. We already have taken up 4, so therefore what we're left with is 1. The s squared plus 4s plus 4 will be a perfect square. In this case, it'll be half of the value of the constant, which was 4, so therefore this will become s plus 2 squared plus 1 is our new denominator. By mapping this to the Laplace transform sheet, we've shown the fact that b is 2 and that omega is equal to the square root of the constant term hanging outside, which in this case the value is 1, so the square root of that is also 1. But looking at this, we hit a little bit of a problem. If we are to substitute omega and b in, what we have is 1, and for this part here, we have s plus 2. The problem is that our numerator for this is 2s plus 1. So what we're going to have to do is find a way to turn 2s plus 1, our numerator, into a linear combination of the 1 and the s plus 2. There are a number of ways to approach determining what the constant should be in front of the 2 terms found in the Laplace transform sheet. One will be provided here. And the methodology works very similar to the concept of partial fractions, where we're having a linear combination of multiple terms such that the numerators are consistent. The easy thing here is the fact that they both have the same denominator, so we don't have to worry about that step. So if we look at what we have here, we have that 2s plus 1 is going to equal a plus bs plus 2b. By looking at this, we see the fact that the only s term on the right-hand side is bs, so therefore that tells us that b equals 2. And what's left with the constant terms is that a plus 2b equals 1, which means the fact that once we substitute in what b is, that tells us that a equals -3. So if we revisit our original equation, with the second term factored out to be more friendly for the Laplace transform table, we can see that when we take the inverse Laplace transform of our second term, that just corresponds to the sine term that we have here. So therefore this term becomes e to the negative bt, where b has been shown to be 2 multiplied by the sine of omega t, where here we showed that omega was 1. And then we include the constant -3. So for our third term, it will correspond to the cosine term, which will be e to the negative bt, which is still 2, multiplied by cosine of omega t, which in this case is still 1. We then add the coefficient to our system, and when we put these all together, we get our final answer, which is that y in the time domain equals 1 minus 3e to the negative 2t sine t plus 2e to the negative 2t cos t. So an important part of dealing with imaginary roots is that you ensure the fact that when you're trying to solve the problem, you are gearing it towards the Laplace transform sheet that you have available. Different transform sheets may show things in slightly different ways, so you're going to want to gear it towards the Laplace transform sheet that is available to you.
You're muted, Dr. D.
So all I was saying is that was exciting, right? You get to do a partial fraction expansion to solve your partial fraction expansion, right? When we have complex roots. Sometimes that happens, and that's fine. We can do that, okay? But let's try an example together, right? So I've got this up here, right? So the first thing we're going to do is we are going to identify the poles of our system, right? The roots of our characteristic equation. And if we solve for our poles here, shockingly, right, we get -3 plus or minus 4j. I say shockingly because we're talking about complex poles, so it would be really, really weird if we didn't get one, right? So what do we have to do, right? So when we get complex poles, we're expecting a sinusoidal response, right? And we remember that a sinusoidal response typically takes the form sine of omega t plus phi, right? But sine of omega t plus phi is really sine of omega t plus cosine of omega t, right? So when we have a sinusoidal or a damped sinusoidal response, we already know that we're going to end up with something that's sine or cosine, or sine and cosine, right? So I want you to keep that in mind, right? And is that cheating, right? Is that cheating? No, it's not cheating. It is understanding what it's supposed to do and then doing the thing that it's supposed to do, right? You took all these classes, you spent all this money to learn things in the classes before this class. We should use those things that we learned, right? We should use those things that we learned. Okay, so what do we do, right? Well, if we look at the Laplace transform table, we know that sine and cosine have very specific look to them, right? So let's look at the, right, so we talked about the poles, right? What kind of response do we expect? We talked about that. So we're going to complete the square, right? Because why? Because we need it to look like it looks in the Laplace transform table, which is like this. So if I complete the square here, right, I'll get s squared plus 6s, wait for it, right? Yeah. I think that's right. Did I do this right? Yeah, okay. Right, we're gonna get this. And we're gonna leave this here like that, right? So I'm just completing the square for the denominator, right? Plus 4 squared, or 16. This can get rewritten as s plus 3 squared plus 4 squared. Right, so this becomes this. And now when we look at our damped sinusoidal constructs from the Laplace transform table, we see that this looks very similar to what we want, right? So comparing these, right, we see that in this case, A would have to equal 3 and omega would have to equal 4, right? By the way that we've written. So what do we do now? We recognize the roots. We know that we're going to have a damped sinusoid. Because we know we have a damped sinusoid, we know we have to have portions that are both sine and cosine added together. So what we do is we take what we've just done here, right? We take our y of s. We say y of s is equal to 2s plus 9 over s plus 3 quantity squared plus 4 squared. And that's going to be equal to a times s plus 3 over s plus 3 squared plus 4 squared plus b times s over s plus 3 squared plus 4 squared. Where did those come from, right? Good question. So just like he said in the video, right? The first one is the cosine term that I wrote down. I need to figure out how, right? I know that this has to be a damped sinusoid. So I'm taking my damped sinusoids and I'm going to see what percentage of this is the sine wave and what percentage of this is the cosine, right? I know A and I know omega from doing my partial on my complete the square, right? Because I put it in this format. So I just rewrote it, right? In the first term, right? This one's due to my cosine. And this one here is due to my sine, right? So now that we have this, what do? Well, we just do the same thing that we've been doing, right? We're going to multiply through on both sides by the denominator, right? Well, let's do that, right? So what do I get? I get 2s plus 9 is equal to as plus 3 times a plus bs. All right, all I've done is I've multiplied through by that denominator. By multiplying through by that denominator, they all cancel, right? Because they all have the same denominator. So now I can set up my equations where I group things, right? So I've got s to the 1. That's going to be 2 is equal to a plus b. I've got s to the 0. That's going to tell me that 9 is equal to 3 times a. Right? Well, that's an easy one. I can solve for a directly, right? A should just be, sorry, I don't know why I put 3 there. Hold on. Please hold. Feel like, yeah, okay. We're good. We're good. I'm reading the wrong part of my notes. I apologize. Oh, that's why. There's no S on that B. Right? There's no S on that B. There we go. No S on the B. All right. Dr. D wrote down the wrong thing, right? Look here. This is the cosine one, right? This one down here, there's no S. It's just B times omega. So I actually don't have the right thing here, right? This should be B times 4. Apologies. I just got so excited, guys. I just got so excited about doing it, and I didn't look at my notes, and then Professor Wingate Bro came, and that's not ever a good thing. So I apologize. You gotta get that guy out of here. Right, so okay, it's even easier though, right? Because now A is obviously 2, right? It's just written there. A is equal to 2. There's A. I can plug that in, right? And I would say 9 is equal to 6 plus 4 times b. So b has to be equal to 3/4. All right, so we get our y of s. And y of s is going to equal 2 times s plus 3 over s plus 3 squared plus 4 squared plus 3/4 of 4 times, or 4 divided by s plus 3 squared plus 4 squared. We can take the Laplace transform of this, right? This guy right here in the blue dashed box, right? That's cosine of 4t times e to the negative 3t. The guy in the blue box, right, is sine of 4t e to the negative 3t. So y of t should be 2 times e to the negative 3t cosine of 4t plus 3/4 e to the negative 3t sine of 4t. The complex roots ones are the ones that take a little bit of time, right? Now, what happens if you have like a complex third order system where you've got a complex root and a real root, right? Well, that happens. Well, you just do your partial fraction expansion, right? You still have to have it, like, that's the example that the guy used in the video, right? You got a real root at 0. Root at 0, typically we get we'll get a constant out for that, right? Guys have any questions on this one? This is a little bit weird, right? So why do we do this way, right? It's not, remember, it's not cheating. It's using your education to your advantage. Okay? You know what the roots are telling you. Do what the roots are telling you. You know what the roots are telling you. Just do what the roots are telling you. If we wanted to do this as a differential equation, right, we could. But solving for a and b is much easier than, having to take derivatives and solve for initial conditions to find a and b. Right? We didn't have to take any derivatives. We had to do some algebra. For the price of a little bit of algebra, you get the time domain solution. No money down, no 0% APR for 6 months, all that good stuff. Black Friday deal, guys. Black Friday deal. All right, you got any questions? Yeah, Asia. Yeah. Mm-hmm. So we're trying to make everything look like these two equations, right? So the sine wave a damped sine wave has the form omega over s plus a squared plus omega squared, and a damped cosine has s plus a, right? And so when we go back to this slide, that's where you just basically plug in your omega and your a value, and then a sine. So think of it this way, right? When you have this damped sinusoid, part of it is going to look like a sine wave, and part of it's going to look like a cosine, right? It just depends, like, how much, right? So you're scaling this by some factor, right? So the sine wave, when compared to the cosine wave, has a very small amount of input, right? Because that's 3/4 of the original sine wave that we had, but we're doubling the cosine, right? So the cosine is going to dominate that response. but the sine wave is still there doing some stuff, right? Applying some phase shift, if you will. We'll talk about later. Any other questions?
Post the solutions for the Laplace transform sheet.
Yeah.
I looked them up, but I still got I got them wrong.
Yes, I'm gonna post them later today. You guys will get them tonight so that you have them for homeworks and stuff. Okay. So can we do this using MATLAB? Can we do inverse Laplace transforms using MATLAB? And the answer is no. So no, we can. Of course we can, right? MATLAB can do everything. MATLAB can solve all of your problems, guaranteed. I don't work for MATLAB, so don't. Anyway, MATLAB, you got to use the symbolic toolbox again, right? So remember, when we did the Laplace, we could take a symbolic function and we could take the Laplace transform of it, right? We can also take the inverse Laplace transform of something. So we're going to rework example 8.8 from the text using MATLAB, right? So what are we going to say? We're going to say sims s, right? So I am using my symbolic toolbox. I'm defining s as my symbol, right? Then I set up my function, right? So y of s is equal to 2s plus 9 over s squared plus 6s plus 25, right? This is the one that we just did. So that will define my Laplace transform, right? Then I Laplace. That is not, it's not a new Apple device, right? It's inverse Laplace of y, capital Y. Although I think Apple is really missing out on large amounts of the market share by not having I Laplace, right? I do think that that's something that they need. So you type I Laplace of capital Y. And if you're so inclined, you can use pretty to make it look nice. And you'll get this out, right? You get 2 exponent, right? 2e to the minus 3t cosine of 4t plus 3/4 e to the minus 3t sine of 4t. Now, some of you are going to come to me with this question next week, and you say, Dr. D, it doesn't look like how I wrote it down, right? Did I get it wrong? And I'm going to say, no, you just got to check, right? Because sometimes MATLAB likes to do this thing where it takes that e to the negative 3t and it factors it out. So it'll tell you it's 2 times cosine of 4t plus 3/4 of sine 4t, the whole thing times e to the negative 3t, right? So just make sure that you notice where they put their parentheses, right? Make sure you're looking at where they put their parentheses. Right? So this is a nice way that we can check what our Laplace transforms, right? Or our inverse Laplace transforms. So I Laplace. All right, look, hey, that's the same answer we just got when we did by hand. So great success, everybody. That's all well and good. That's all well and good. But how do we actually, and this will probably be the last thing we do today, right? How do we actually use this to analyze a dynamic system, right? Because so far, we can do the Laplace transform, right? I can do some stuff to it and I can invert it, but like how do we use this to our advantage, right? How do we use this to our advantage? So there's 2 things that we can do. Right? I'm going to group this into 2 categories. There's 2 ways that we can solve systems using Laplace transforms. The first is apply the Laplace transform to the system in the time domain, like we just did, right? So we did one, right? We have this system, we know what the input is, we take the Laplace transform on both sides, we rewrite it, we solve for y of s, right? And that's fine. But the other way that we can do this is using a transfer function. Now, what is the difference between using the overall Laplace transform and the transfer function, right? So by the way, side note, if you are asked to use the Laplace transform method to solve for a system response, that is asking you to do it like take the Laplace transform of both sides using the initial conditions, solve for y of s, right? Do your partial fraction expansion, and then use your inverse Laplace transform, right? That's what it's asking for, right? So that's method one here, right? This is method one right here. And this is method two, using a transfer function. So how are they different? Well, the only difference is that if you're using a transfer function, you are assuming zero initial conditions. That is what you are assuming, right? So the first method yields a complete response because the initial conditions can be incorporated, and the second method yields the response due to zero initial conditions, right? So if you're using the transfer function method, you assume that the initial conditions are zero. Okay. What if you're given a function with some initial conditions and then you're asked to find the transfer function? You should summarily ignore those initial conditions and put zero. Whenever you are asked for a transfer function, that automatically in your brain, please have a light turn on that says zero initial conditions, right? Laplace transform for a transfer function. Transfer function, zero initial conditions. Transfer function, zero initial conditions, okay? So what are the basic steps for using Laplace transform method to obtain a solution? First, take the Laplace transform of every term in the input-output equation and include the initial conditions, right? This step will convert an ODE into an algebraic equation with the Laplace variable S. Then we solve this for our output, whatever our output happens to be. In this case, we used y of s, but it doesn't have to be y of s, it's whatever our output is, right? Then we take the inverse Laplace transform of y of s, most likely needing to use partial fraction expansion unless we get really lucky and something falls out, to obtain the time response y of t, right? So take the Laplace transform, we mess around with it using algebra, and then we take the inverse Laplace transform. Now, I will present to you the formal definition of a transfer function. Okay. So we did an example of that, right? We did an example of the Laplace transform method, the first one that we did in class today, right? Where we had our ODE and we did the Laplace transform of it and we incorporated our initial conditions, right? So a transfer function, g of s, is defined as the ratio of the Laplace transform of the output y of s to the Laplace transform of the input u of s with zero initial conditions. So this is, I want you to hear this right now. Before, when we were told that we had a step input, we took the Laplace transform of it. If you are finding the transfer function, do not take the actual Laplace transform of u of t. Leave it as u of s. Okay? And I'll show you for why right now. I'll show you why right now. Quick example, y double dot plus 8y plus 10y is equal to 4u dot. I want the transfer function. Remember, transfer function, right? It's telling you that g of s is equal to y of s over u of s. This is what my transfer function is, right? I need to take the Laplace transform of each of my terms. Now remember, there's zero initial conditions, right? So all of those terms in my derivative, where I had like s squared y of s minus the initial condition times s minus the velocity initial condition, those are all zero now, right? So what happens? This is zero, this is zero, this is zero, right? That's zero. All my initial conditions are zero. All my initial conditions are zero. Right? Set all my initial conditions equal to zero. Well, this just got really interesting. because I end up with s squared plus 8s plus 10. Hey, isn't that just the characteristic equation of the system? Is equal to 4 times s, right, because we have a dot, times u of s. And if I divide by u of s and divide by s squared plus 8s plus 10, I now have the transfer function. But if you took the Laplace transform of the input before doing the transfer function, you would not get the transfer function, right? Because remember, what is the power of the transfer function? The power of the transfer function is that y of s is equal to my transfer function times the Laplace transform of u of s. So if we wanted to do it this way, we could solve this using a transfer function as long as I know the Laplace transform of u of s. But I leave it general to begin with because u of s can literally be anything, right? U of s could be anything. Do we have enough time for this one? Maybe. Okay, so this is a real transfer function. How is it different from the time domain transfer function? You use s instead of d, right? But this is the actual definition now, right? Before we kind of just used it to make a point about block diagrams. Right? This is the real transfer function. Okay? The basic steps for using the transfer function method to analytically obtain a system's dynamic response are the following. 1, derive the system's transfer function. So if you're asked to, use the transfer function method, you should probably find the transfer function. That would be a good place to start, right? Find the transfer function. 2, multiply the transfer function times the Laplace transform of the input, right? 3rd, take the inverse Laplace. So you get the transfer function, then you multiply your transfer function by the Laplace transform of u of s, right? Then you do your partial fraction expansion, and you pull out your coefficients, right? And then you use the inverse Laplace transforms from the table. This is super powerful, right? Transfer function method is very powerful. It allows us to test input responses that are varied and very quickly, right? Allows us to do it very quickly. As long as we know how to take the Laplace transform of something and then invert it, we're gold. Do we have enough time to do this? Let's see. Because this one, we've got to go all the way through, right? We don't have a model. We've got to make a model. So the figure below, or next to this, shows a single disk mechanical system where the motor provides a torque T in directly to the rotor inertia J. I want the angular velocity response of this mechanical system if the rotor is initially spinning with omega of 0 is equal to 120 radians per second, given to us in RPM as well. And the input torque is a step function of magnitude 15 Newton meter applied at t greater than 0. The rotor moment of inertia is given, right? J is 0.4 kilogram meter squared. And the viscous friction coefficient is 0.06 Newton meter second per radian. So we got to find the model. Right? I'm not going to run through the whole process for modeling this right now, for the sake of time. We've seen this system before, right? If we want it in terms of, right, this particular system, we want it in terms of the velocity, right? We'll end up with J omega dot plus B omega is equal to T in of T, right? So this is a simple first order system with respect to velocity. Okay. If you have questions about how to make that model, please come to office hours and we can discuss it, right? But for right now, I'm going to assume we've done enough of these that people can suss out how to get this particular model. So there's my equation, right? So what do I have to do? Right, J omega dot plus B omega is equal to T in of T. Well, Laplace, right? Take the Laplace transform here. If I take the Laplace transform, I'll have J times S of omega. Right, that's a capital omega. The horseshoe looking thing's a capital omega. I swear, it's true. 100% true. Minus omega of 0 plus B times omega of S is equal to, well, what were we told? What were we told that this input was? Right, we're told it's a step, right? It's a step of 15 Newton meters, right? That's 15 over S, right? Remember, a step is a constant input. Constant input of 15. The Laplace transform of a constant is 15 over S. What if you don't remember that it's 15 over S? Well, you go to the table, right? You know it's a constant. Step is a constant. Laplace transform of a constant is the constant over S. I can plug some values in here, and in doing so, I'll get 0.4 S omega of S minus 0.4 times 120 radians per second plus 0.06 omega of S is equal to 15 of S. Okay, so I'll group my like terms, right? I'll get 0.4 S plus 0.06 times omega of S is equal to 15 over S plus 48, right? Where's that plus 48 coming from? 120 times 0.4 is 48, right? In order to get it to the other side, I have to add it, right? I will make this 48S plus 15 over S, though. And I will change the denominator. Well, I'll provide a common denominator. I'm not changing it. I'm using a common denominator. I can solve this for omega of S. That's going to give me 48S plus 15 over S times 0.4 S plus 0.06, right? And now what? Well, now I'm going to pull out, right? I'm going to pull out this 0.4 from here, right? So I factor a 0.4 out of here, right? Out of here and here. So I divide this term, right? I'm going to take 0.4 out. I'll put it out in front, right? And if I do that, well, that gives me, I can divide the entire numerator by 0.4, right? which gives me this. And I think we all see where this is headed, right? These are two distinct real roots. So we will partial fractionize this, right? So this is A over S plus B over S plus 0.15, right? And we can run through this. Okay. Right, so now what, right? Now what? Good question. Now what is, we multiply everything by S times S plus 0.15, right? We're going to multiply everything by this denominator, S times S plus 0.15. And in doing so, I'll get 120S plus 37.5 is equal to AS plus 0.15A plus B times S plus B times S. Right. Put all my S terms together. Put all my S to the 0 or my non-S terms together, right? So S to the 1 terms, bless you. 120 is equal to A plus B. S to the 0 terms, right? 37.5 equals 0.15A. Well, I can solve for A pretty easily, right? A is equal to 250. I can plug that into my other equation and solve for B. B is going to be negative 130. If I wanted, right, so then I'll plug that back in for A and B in the above equation. Right? Plug that in for A and B in the above equation. Right, so we end up with Y. I know you can't see what I'm writing, at least if you're at home. Right, I'm leaving it up for a second. We get Y, or not Y of S, sorry, omega of S is equal to A over S plus B over S plus 0.15, right? There, now we're all on the same page. So this is equal to 250 times 1 over S plus negative 130 times 1 over S plus 0.15. So what is my inverse Laplace transform for this? (250 minus 130 e to the negative 0.15 t). That's what Kat says. Does everybody believe Kat? I'm getting some thumbs up. Good job, Kat. Nailed it. Nailed it. That's it. So, the long way, right? We make them all. We take the Laplace transform. We do partial fractions. We take the inverse Laplace transform. That's the long problem, right? Today we didn't make the model in the interest of time. Could you check this? Yes. You have initial conditions, right? You could plug in those initial conditions to check. You know what omega 0 is. You could totally do that. You guys have any questions right now? Won't do that. We'll save that for save the rest of it for Tuesday. Next week on Tuesday, we'll enter the realm of impedance, right? And then on Thursday, we will do a bunch of problems related to Laplace transforms. Okay? You guys have any questions right now? Okay.
No, sir.
All right. Well, we're gonna play a game. I know I said that we weren't gonna do this on today, but I changed my mind because we're gonna play a game. So you guys are gonna want to talk about this in Discord, right? So this is Jeopardy. If you guys don't know how to play Jeopardy, I feel bad for you. It's a trivia game where you answer in the form of a question, right? So you will be given the answer and you have to tell me what the question is, right? All right. Okay, let's see how this works. All right. First, you will get one Jeopardy song to wager your points. How many points do you have? I will tell you in a second. Don't worry. You get one Jeopardy song to do that. Okay? No. Okay? The host of Jeopardy did pass away last week. It's true. Alex Trebek, 80 years old. Once you've locked your points in by putting them into Discord and saying these are the points that we are wagering, you will see the answer, and then you'll get two Jeopardy songs to provide your question. Put your question into Discord saying this is, right, make it very clear what it is. Once the music is done, I will require one person from each group to read the answer provided in Discord, and then the points will be updated on Monday. Okay, so I gotta get the right mouse. Right? Here are the points. Okay, write down your points right now. Somebody on your team. I'll give you a second. Then I'm going to give you the category, and you're going to have to do the thing. Okay, everybody should have their points. If not, you could also type exclamation TQ points in the Discord to get them. All right, well, that'll only give you first through third, so make sure you got them. All right, and your cat, oh, no. Did I not put it? No, thank you. Hold on, please hold. Don't do that yet. No. Did I put this in the wrong spot? I know I put it in. Oh, interesting. Please hold. Your patience is appreciated. Maybe we aren't doing this today, I guess. Maybe we aren't. I totally put this in last night. I must have put it in the wrong day. Here. Okay. Where did it go? Come on. Hold on. I saw it. I saw it for a second. It's being real jerk right now. Yeah, it was in there. Why was it skipping? Okay. Here's your category. It's engineering. All right. I'll give you 1 minute. 1 minute. All right. I can't play the song, otherwise it'll blow up a feedback loop in the classroom, possibly the whole campus. I apologize. Put your point in your team's Discord channel.
Does it have to be like an app points or?
No, you just somebody from your team, just type them in there. It's fine. Remember, right? All right, you guys are 30 seconds. 30 seconds to get them points in.
Wait, where are we typing them?
Into Discord.
In the class channel or
if we get
on like our
question
group?
wrong, do we lose points like on
team
Jeopardy? Do we get them like taken away from our total points for next week?
If you get it wrong, yes, you lose the points that you wagered. And before anybody gets any ideas, right? There's no such thing as wagering negative points and then getting negative points subtracted from your score, okay? Because you plan on getting it wrong. That's not how it works.
Do we put it in the 945 chat?
Put it in your team chat.
Oh, you can see it? Okay.
Yeah, I can go into all the team chats. All right, guys. 5, 4, 3, 2, 1. All right. Excellent. It looks like. All right. Here is. Uh-oh. No, wait, please hold. All right. It was the Persians, not the Dutch, who invented this energy-producing machine to grind grain. I will give you 2 minutes to answer in the Discord. 2 minutes. One more. I know we're over. I apologize. Technical difficulties, all that. Once you guys have your answers in the Discord, we don't have to go through and read them. I'll just post what this thing is and I'll tally the points, right? So right now is the time. Put your answers in the Discord. Right. Right now. Yes, remember to answer in the form of a question. Okay. Okay. All right, looks like everybody's got their answer in, and the answer is, what is a windmill? A windmill. The windmill, a windmill. Okay. Well, we'll see what happens with that on Monday. Good job, everybody. Here we go. Right. Sorry for going over. Sorry for going over. Remember, if you're on the lower half of things, please make sure you come by office hours, right? We got to talk. Make sure you come. 3 to 5. Tuesdays, Wednesdays, and Fridays, 9 to 11 on Mondays, right? And here's the final one.
We'll do more example problems because that was my question on how we apply like Laplace to the like spring or dampness like systems. Okay.
We're gonna do more more stuff. There's going to be a lot of both circuits and mechanical system problems that we're going to do. Remember, if you have the second order differential equation, but it's just, you have to just take the Laplace, right? It doesn't discriminate against elements, right? It's just whether or not you're taking the second derivative, the first derivative, or not.
Okay. Regardless of what the.
Regardless of what the system is, right?
Okay.
Right.
Thank you for pushing the lab back to, I don't know.